Okay, moving towards graphing rational functions fractions. And specifically, a rational function is a polynomial over polynomial. These could be, so these instructions could be extended to something that's a little more general than a rational function, but we'll just say rational function slash fractions. Once we put a fractional form in there, that opens up the door for asymptotes. The two graphs that we did previously weren't fractions. That wasn't a fraction. And this first guy, not a fraction. And so we didn't talk about asymptotes. We're only going to talk about asymptotes in conjunction with original functions that have a fractional form. That's the only time you open up the door for asymptotes. Now, just because a function has a fractional form doesn't mean it will have an asymptote. It just can. There are actually three types of asymptotes: vertical, horizontal, and oblique. We're going to confine our discussion to vertical and horizontal. So talking about vertical asymptotes first. Consider f of x equals x plus 2 over x squared minus 4. Recall a rational or fractional function is undefined at any number that causes the denominator to become equal to 0. So our first simple little thing, find where f of x equal x plus 2 over x squared plus 4 is undefined. And so we just merely set that denominator equal to 0 and solve. So I get x squared equals 4, x equals plus or minus 2. And then I have the graph for you. We have an asymptote at x equal 2, and we have an open circle at x equal negative 2. Remember, an open circle is our graphical representation that there is a single missing point there. And then I got lazy with my arrows, and I did not put arrows there. But my point here is that just because my function was undefined does not mean you have a vertical asymptote. There are two possibilities when you have a rational function and the denominator becomes 0. There are two possibilities: a vertical asymptote or a hole in the graph. And I've seen many, many things out there on the web, and I've seen other teachers actually say, oh, if your denominator is 0, you've got a vertical asymptote. No, that's not true. Your denominator is 0, you either have a vertical asymptote or a hole. What makes this one a vertical asymptote calculus-wise is that the graphs, or the limits, as I go to x plus, let's go in so we can see it better. There we go. As we go add the limits, as x approaches 2 from the left and x approaches 2 from the right, the limits go off to infinity. And so that's why we get a vertical asymptote. Whereas over here, I don't have the actual number here, and if I was smart, I could figure out what the actual number is. I think it's 1/4, that my limit as I approach negative 2 is about 1/4. And so since my limit exists, I just get an open circle. But over here, because the limits go off to infinity, that's what causes that vertical asymptote. So there are really two things. You need the denominator to be 0, and then you need the limits to shoot off to infinity or negative infinity, as the case may be. Now, in general, a vertical asymptote is a vertical line that guides a graph nearly straight up or down. A vertical asymptote is never crossed or touched by the graph, because first and foremost, the function was undefined there. If the function is undefined, there's not going to be a point on the graph. A vertical asymptote really is just an imaginary guideline. It's just telling us, it's just showing us what's happening to the function on either side of it. It's really just kind of a guideline. That's never crossed or touched by the graph. The equation of a vertical asymptote is an x equal number. And I'm just a little picky there, that if I ask for the equation of the vertical asymptote and say, was this problem, and you just write down 2, you aren't going to get full credit. A vertical asymptote is a vertical line. Vertical lines have the form x equal number, so x equal 2. Now we are going to just use algebra to find vertical asymptotes. So how to find vertical asymptotes? Oops, went the wrong way. There, that's pretty good. How to find vertical asymptotes. Note, again, asymptotes are only possible for rational functions. 1, find where the original function is undefined. 2, for each number found in step 1, verify that the numerator of the original function will be non-zero. 3, for each number that satisfies steps 1 and 2, each number that satisfies steps 1 and 2 will yield a vertical asymptote x equal number. And 4, good habit, check by graphing. We are just going to use algebra here. So doing this, so step 1, where the original function is undefined, and we already did that, plus or minus 2. Then step 2, I take each one of those numbers and I plug it into the numerator. The numerator that happens to be x plus 2. And I'm going to get 2 plus 2 or 4. Now I don't care what the number is at all. Yes, I get 4, and right now I'm going, not that that's wrong, but I'm going to white it out, and I'm going to write non-zero. And then doing the same thing with negative 2, my numerator, which happens to be x plus 2, would be negative 2 plus 2, which is 0. Then step 3, or what I wanted here, for each number found in step 1, verify that the numerator of the original function will be non-zero. That guy's non-zero. So at step 3, we have a vertical asymptote at x equal 2. And here's why I just wrote non-zero. A common mistake, if I'd left the 4 there, lots of people are going to tell me x equal 4. This number here, it happened to be 4 yet, it happened to be 4, but it has no meaning other than it was not 0. And so it wasn't important that it was 4 or 12 or 92. What's important is not 0, and we get x equal 2. So there's my vertical asymptote. And just note that because this was 0, and it didn't ask for this in any way, shape, or form, but there's a hole at x equal negative 2. That when you plug into your numerator and you get 0, that tells you had a hole. Now, we didn't ask for that, but I just thought I'd throw that in there, that there was a hole. And then we already checked that on a calculator. We already saw that. Okay, next guy. So set that denominator equal to 0. And remember, and I should solve it correctly. That's going to be negative 16. And so I'd get plus or minus the square root of negative 16, which is imaginary. And we are not using them. We're not using imaginary numbers. And so we had no real solution. And so this guy has no vertical asymptotes. And so like I said, just because it is a fraction doesn't mean it has to have asymptotes. And then you could check that by looking at a graph on your calculator, and I will leave that up to you. So there's what we have for vertical asymptotes. So like I said, there are 3 types of asymptotes: vertical, horizontal, oblique. We aren't going to talk about oblique, so that leads us into horizontal. So horizontal asymptotes. So there I have a graph down below. I have f of x equal x squared plus 2x plus 1 over x squared plus 1, and there is that graph. And this line that goes right in the middle here, at y equal 1, that's going to be my horizontal asymptote. And that's what it says down there. It appears on the extreme left and right sides of the graph are near y equal 1. Y equal 1 is a horizontal asymptote. And note, the graph is crossing the horizontal asymptote. It happens to cross right about there at the point 0, 1. Horizontal asymptotes, and it's down here, in general, horizontal asymptotes are horizontal lines that guide a graph on the extreme left and extreme right sides of the graph. If a function has a horizontal asymptote, it can be thought of showing where the graph begins and ends. Horizontal asymptotes have no impact on the center of the graph. Horizontal asymptotes may or may not be touched or crossed by the graph. Equations of horizontal asymptotes have the form y equal number. And again, I'm going to be picky, that if I ask you to give me the equation of the horizontal asymptote and you just write down 1, you aren't going to get full credit. Horizontal asymptotes are horizontal lines. Horizontal lines have the form y equal a number. Now, some important things here. They only tell us, and it says in there, it really only tells you when a horizontal asymptote exists, it really only tells you where to begin and end. It tells you absolutely nothing about the middle of the graph. And so anything can be happening in the middle. Maybe the function crosses the horizontal asymptote, maybe it doesn't. Maybe it crosses 27 times, 26 times, 932 times. You just don't know anything about the center of the graph once you know about horizontal asymptote. All a horizontal asymptote really tells you is where to begin and end. How to find horizontal asymptotes. Find the limit as x goes to infinity of f of x. If the limit exists, there's a horizontal asymptote at y equal limit answer. If the limit does not exist, there is no horizontal asymptote. Now, I did just say as x goes to infinity. A disclaimer. It is possible for a graph to have a left horizontal asymptote that would be denoted by x goes to negative infinity f of x, and a different horizontal right different right horizontal asymptote that would be determined by the limit as x goes to infinity. That you can have different left and right asymptotes. So if we were going to be perfect mathematicians, we would find two limits. The limit as x goes to negative infinity and the limit as x goes to infinity. In this class, however, the problems discussed will never have different left and right asymptotes, so evaluating only the limit as x goes to infinity of f of x will be sufficient. Calculus 1, you can get by, in my class, Calculus 1 in Mrs. Brazelton's class, you can get by just, for horizontal asymptotes, just looking at the limit as x goes to infinity. Greater mathematics, maybe someone else's class, you might need to do both as x goes to infinity, as x goes to negative infinity. We've seen tan inverse before. There's the graph of tan inverse. And notice it has a right horizontal asymptote of y equals pi over 2 and a left horizontal asymptote of x equals negative pi over 2. And this graph is going to creep up in your future, especially if you go on to calculus 2, you will see this. So it is very possible for a function to have different left and right horizontal asymptotes, just not in this class. And I think we'll end this video here and then find some horizontal asymptotes in the next video.